All right, I want to take a look today at ANOVA, analysis of variance, and see what this test is all about. Kind of explore the assumptions and the purpose of the test, and also to discuss why we would use this test over other tests. And also I want to get into the conceptual nitty-gritty of the test itself. All right, so I'll post these notes so you can read them alongside the presentation here. So basically the purpose of ANOVA is to determine if there's a mean difference in our treatments. So in other words, if you had a sequence of treatment groups and we apply a varying level of that treatment to each group, we want to know if there's a difference between any of the groups, not just between specific groups, but any of the groups. Why else might we be doing this? Well, it's always an issue of having a false positive, so we want to minimize type 1 error. And you might be thinking, well, why don't we just apply some repeated use of the t-test, for example? But the issue that we run into there, well, if we use the t-test a bunch of times, we actually build up type 1 error. And so we'll kind of come back to that idea in a moment. There's some key assumptions that go along with using ANOVA. The first assumption is that all samples are independent. Really, that basically just boils down to you can't have members of multiple groups. So for example, if you're testing people's opinion or their preference for different learning options, you can't have the one person in multiple groups, because their opinion of the first treatment, which they didn't like, is directly tied to their opinion of another treatment which they did like. So we have to make sure that the samples are independent. These other two are I don't know, we kind of gloss over them, hand wave them through, but all samples we're assuming have the same variance. We're assuming that they're coming from the same population, so if they come from the same population, they should have the same variance. The other thing is we're assuming that the population are normally distributed. I wrote samples, but I meant to say that each group is coming from a normally distributed population. Okay, so yeah, why are we using ANOVA instead of multiple t-tests? First up, we want to minimize type 1 error. Each time you run a t-test, you have maybe, let's say you pick an alpha of 5%. So we're allowing 5% possible type 1 error. Well, every time you run a t-test, let's say you're trying to compare 3 different means, the first comparison between mean 1 and mean 2, between mean 2 and mean 3, and then mean 1 to mean 3, you have 3 different occurrences of type 1 error. And so the probability of type 1 error actually builds with each successive use of the t-test. So testing everything all at once allows us to minimize type 1 error, but we also kind of already said that, we also can compare more than 2 groups. So we're able to say, okay, are all means equal, or are they all not? So our hypothesis, we're able to determine this mean by saying, okay, let's assume that there's no difference. So we're saying that all means should be the same. Okay, and what this means is that instead of picking a specific alternative hypothesis, we're not saying, oh, mean 1 is bigger than mean 2, for example. That would be a t-test. What we're doing is we're saying, okay, let's just take the fact that if they're all equal, that's one idea, or what about not all equal? So we're not going to peg down a particular alternate hypothesis. All right. What does that mean for us? How do we do this? How do we establish that there is a mean difference? Well, basically what we're going to do is look at the variation. So envision 3 columns with multiple inputs in each column. We can compare the variability between the columns, or in other words, between the groups of treatments, and we can also look at the variability within each group. So what we're trying to do is establish if there's a difference, or if the variabilities are identical between the variability within each group to the variability between the groups. Why are we doing that, or what's going on with that? The idea is to look at the variability between the groups. That'll essentially be the variability of the means of each group. Okay, and we're going to see if that is close to the same as the variability, as the average variability within the groups. Okay, so if they are identical, that means that there's really no influence from the treatment. Okay, so the variability of the mean should be the mean of the variability if these are independent events and if they're identical. So we want to explore that and kind of build the criterion for truly testing that. And the way we do that is we can look at what we call the F statistic. Sometimes it's called the F ratio. Okay. Now the F statistic, what it is, it's a ratio between the variance it's a ratio of the variance between to the variance within. And what does that mean for us? The variance between the treatments, like I said, would be looking at how do each average of each treatment group compare to the other averages, and then we want to essentially look at the variance, the mean variance between all the individual groups. Okay, the closer f is to 1, the more likely the treatment has no effect. Okay, and it makes sense if two things are equal. For example, 5 is equal to 2 times 2.5. If we look at the ratio, well, 5 divided by itself is just 1. Okay, even if it comes in different forms, a ratio of a number with itself is just 1. So the closer f is to 1, that means the closer the two variances are to being identical. Okay, let's take a closer look at this variability idea. Okay, so there's varying types of variability, and what does that mean for us? Well, essentially, the variability, it doesn't always come in the same form. Okay, so if you're comparing multiple groups, this idea of the variance between treatments, what we're doing is actually looking at the averages of each treatment group and then comparing those to the overall average, right? So we assume that all sample elements come from the big population, and if we compartmentalize them into different groups, if they all are essentially the same measurement, then we should expect that the variability between the averages of each group matches up with the average variability of every element compared back to the center line, the grand mean, let's call it. So the variability between the treatment groups is just the variance of the means, and the variability within the treatments is just the mean of the variances, right? So we kind of assume that all sample sizes are the same. The formulas work out cleaner if we do that. We don't have to have the same sample size. For example, if you're comparing the dosage of a certain medication, and in one level of that dosage you have 10 patients, and another you have 15, that's okay. We're still going to be able to compare them using ANOVA. But just in kind of the setup for the formulas, it's easier at the beginning to assume that all sample sizes are the same. Now, since we're dealing with variance, we're talking about comparing variance and variability and things. That means we also need to talk about degrees of freedom. So the F statistic is comprised of a ratio of two variances, each that have their own degrees of freedom. So really what that's saying is that F, in order to truly describe the distribution of this F statistic, we need to talk about two different degrees of freedom. The first being the degrees of freedom associated with the numerator, and the second being the degrees of freedom associated with the denominator. Okay, so since we're dealing with calculating the mean, the variance of the means for the numerator, think about having k distinct groups. So we have k distinct means. When we calculate variance, right, and think back to the formulas, sums of squares and things like that, but we divide, to find the variance, we divide by the degrees of freedom. In that case, we always take the sample size and throw out 1. Right, because the variance can be found by having 1 less than the number of observations. So with that, if we have, for example, 5 different treatment groups, we can find the variance of those treatment means by looking at only 4 of those treatment means, and if we knew the grand mean, then we could figure out the 5th one. So what that tells us is the number of groups that we have, k, if we take away 1 from that, we would pick up the degrees of freedom for the numerator. Now, for the degrees of freedom for the denominator, we are talking about essentially the sums of the variances, but really it's the average variance. And so what that tells us is in the average, and computing the average, we're looking at the sum. So what that tells us is that degrees of freedom for the denominator is actually going to be the sum of the individual variances that we have making up that variability calculation. So each one of the group treatment groups has its own degrees of freedom, n-1 for each one of those. And so if we have k groups and they're all the same sample size, if you add those all up, what you do is each one of the groups adds up to the total amount, the population, or the number of each group adds up to the total population. And if we are adding k groups up, that means we're going to be adding up k copies of -1. So in other words, we take the number of observations and we partition it into k groups, and so that's why our degrees of freedom for the denominator is n minus k. What that means for the F statistic is when you find when you go to use, for example, a table to find the value of the F statistic, you need to be equipped with both of these. It's important to recognize that if I add these degrees of freedom together, I get the total degrees of freedom, which would be n minus 1, big N minus 1. And that's important because if we're looking at variance of everything all together, so the grand total variability of your data set, the degrees of freedom have to add up to n minus 1.